let's look at a couple of more things about the entropy. Now, the entropy is defined, delta S, as the heat flow during a process divided by the temperature. So this QREV, this means reversible. So the entropy is defined as being the heat flow during a reversible process divided by the temperature. And a reversible process is a process that happens so slowly that at any point it can go either direction. So if we wanted to, say, compress a piston, so we have a cylinder here with a piston in it. So this is our piston here. And we have a cylinder. If we wanted, and we have a gas, say, here. If we wanted to compress the gas, we could just drop a big weight on top of the piston, and the piston would move down suddenly. But if we wanted to do that infinitesimally, what we could do is we could drop a grain of sand on top of the piston. The piston would move ever so slightly. We couldn't even see it. Then we take a second grain of sand and drop it on there, and a third grain of sand, and then we keep doing this. And so then we have this pile of sand that eventually builds up, and the piston will eventually have moved to a lower position, compressing the gas. So this is a reversible process, a process that happens so slowly that we have infinitesimal changes. So that's what Q reversible stands for, a process that occurs so slowly that the heat flow occurs infinitesimally. So if we have delta S for the universe, we know that this is delta S for the system plus delta S for the surroundings. And we can write delta S of the universe is equal to, now we use our definition of the entropy for delta S of the surroundings. So this is Q reversible over the temperature. Now, Q reversible, if it's done under conditions of constant pressure, is delta H, the change in the enthalpy. So this is delta S for the system plus delta H. Now this is for the surroundings divided by the temperature. Now if we instead want to use delta H of the system, heat flows between system and surroundings, so the heat of the surroundings will just be the negative heat for the system. So now we have delta S for the universe is equal to delta S for the system minus delta H of the system divided by the temperature. Now let's multiply both sides of the equation by T. Now T will cancel there. And we'll multiply by -1 on both sides of the equation. And so now we have negative T delta S of the universe is equal to delta H of the system minus T delta S for the system. So we can see if delta S of the universe is positive, then we'd have minus T delta S. So this product is going to be negative. So for a process that occurs, T delta S of the universe is going to be negative here. So if we let delta G represent negative T delta S of the universe, then we have delta G is equal to delta H of the system minus T delta S of the system. So now, if a process is spontaneous, delta G will be negative, and if it's not spontaneous, it will be positive, because in order for a spontaneous process to occur, delta S has to be positive of the universe. And so we have the positive number, a positive temperature, times the negative sign. So delta G will be negative for a process that's spontaneous, and it will be positive if delta S of the universe is negative. So the reaction, that process, will not occur.